Um, okay, so welcome back to the fifth lecture on polymer physics. And let's discuss what we had learned up till now in the last 2 weeks. So basically, a linear polymer chain is an extremely complicated object. It apparently looks very complicated with multiple degrees of freedom, which can take all possible conformations. And what we started off with saying that, okay, let's say, assume that a linear polymer chain is basically doing a random walk in 3D space, and then we can talk about the mean extent of the polymer chain, right? And then we realize that, okay, but really all polymer chains are not, first of all, uh, basically each bond vector cannot possibly do a random walk in space. There can be restrictions due to bonds and presence of monomers and angular direction. So we decided to come up with the idea of a Kuhn segment, so that if you look at a long polymer chain at length scales larger than the Kuhn segment, you can consider it at that length scale to be a flexible polymer chain, where basically the Kuhn segments shall be the new coarse-grained effective monomers of a polymer chain. Furthermore, we realize that basically uh, now there can be correlations between bond vector, and the correlations between bond vectors decays at the length scale of around the persistence length. And furthermore, we figured out that the Kuhn length is basically approximately double the persistence length. We had been using the random walk model, the statistics of end-to-end distance vectors, and what is the distribution of end-to-end vectors in the polymer chain. But then we also discussed that, I mean, an estimate of the polymer size from the end-to-end vector might not be an appropriate way, or a good estimate of the size of the polymer chain, and hence we introduced the idea of the radius of gyration. And radius of gyration of a polymer chain, which gives estimate of the extent, and statistically averaged uh, extent of the polymer chain. So that is related to the n to n vector, uh, statistically averaged again, of the polymer chain. So the mean square end-to-end vector square of the mean. So the mean of the square of the end-to-end vector, right? So that's the REE. But throughout we have been considering ideal chains. That means that you assume that each monomer can occupy zero volume in space, and as a consequence, basically not only that monomers can sit on top of each other, but bond vectors can be in any direction, and moreover, chain crossing was allowed, as it comes from the random walk model. But we know that in reality that is not possible, and now we shall take the first steps to try to incorporate corrections to the ideal chain model. And that is basically the Flory theory, when you incorporate the effect of excluded volume. So what is excluded volume? So two monomers, they occupy a finite volume, and so jth monomer, which might be far away along the chain contour from monomer number I. So basically the polymer can bend in 3D space, and it is possible that the jth monomer might want to occupy the same position in 3D space as the ith monomer, but that is not allowed. That volume is excluded. So the jth monomer cannot access the volume which is already occupied by monomer number I, and vice versa, of course. And so basically some volume is excluded, and that is the basically excluded volume effect. Right, so we're going to incorporate that, and a consequence of excluded volume effect is also that two polymers cannot cross each other, or if you want to talk in terms of the language of random walks, you have a self-avoiding random walk. Okay, so these are the things we're going to discuss in today's class, and the framework of this discussion is the so-called Flory theory. I want to emphasize that Flory theory is a mean field theory. We will be talking in the mean field language. We are going beyond the ideal chain. And just at this point, I shall also want to emphasize that yes, we are going beyond the ideal chain, but we still have the assumption of good solvents. We assume that the monomer is in a very good solvent, so there's no energy cost, there's no energy penalty for monomer to be in contact with the solvent. It is not that the monomer prefers there's a energy cost or a energy gain in being contact with the solvent. So we are not considering solvent effects here. So in one of the next classes we shall be incorporating the interaction between the monomer and the solvent, and when you incorporate that in the theory and decide what the conformations of polymers will be, so that is called the Flory-Huggins theory. So the word Huggins comes in, but here we are looking at a dilute single polymer chain, going beyond the ideal approximation. We are not incorporating uh, solvent effects, or rather we are considering that the solvent is a good solvent, so there's no energy cost for the monomer to be in contact with the solvent. So basically, so there are two components, there are two aspects of the Flory theory. So first of all, we have to discuss the entropic forces, or what are the free energy cost for a polymer to be in a more stressed configuration, right? And why do we want to consider this? I mean, the free energy costs for stress polymer configuration, because if two monomers cannot sort of sit on top of each other, or there are excluded volume effects, then basically I mean, the corresponding language would be a self-avoiding random walk, and the consequence will be that the polymer as a whole will be in a slightly more stretched configuration compared to what is allowed by ideal random walk. Okay, so basically this entropic forces of stress is entropic forces due to stretching, and the energy cost due to self-avoidance, excluded volume. So they will compete against each other and give us a revised size estimate for the size of a polymer chain, a single polymer chain, a dilute polymer chain in a good solvent. Okay, so this basically sets up the framework for today's discussion. Okay, just to remind you, we are considering an still, so an ideal chain considers no energy for overlap, but when calculating basically this entropy cost, we will be assuming the ideal chain, but otherwise we will be also considering energy for overlap. We are not considering any energy for bending, so we are looking at length scales above the Kuhn monomer. So we have a so all angles are, so all conformations have the same energy, sharp bends are allowed, and no solvent monomer energy cost. Okay, so we are basically discussing this part right now. So so what is the entropy of a polymer chain with n monomers? because there's no energy for bending. So energy is fixed, zero if you like. And so the entropy is kb into ln omega, where omega is the number of microstates. And what is microstates? Here, each microstates corresponds to a different conformation of the polymer chain, right? And we can also calculate the entropy with n monomers, but the number of microstates which are allowed when you have a fixed end-to-end vector in R, right? So then entropy for S and R will be Kb log number of microstates which are allowed for this particular value of the end-to-end vector. And of course, if you integrate over all these omega and R, you will get this total omega. Now, if you want to specify a particular end-to-end vector, so the number of microstates which are accessible are of course less than the total number of microstates for this omega. And then you say, okay, what is the probability? What is the 3D probability that polymer chain takes a conformation such that the end-to-end vector is a fixed value in R. So, or if you're talking about, so that's what you would talk about when you have a discrete model. But in the continuum limit, you will be talking about the probability density, and then P3D is the probability density, and basically the probability is P3D into dr, which is the probability of finding polymer in different conformations such that the end-to-end vector is between R vector and R plus dr vector, right? So this probability density, if you like, is given by the total number of conformations possible with R vector and divided by the total number of conformations where you have no restrictions in the end-to-end vector, except that the contour length of the polymer, of course, should be maintained, right? So the contour length R max has to be n into b, where b is the bond length, or if you like, the Kuhn segment, right? So this is a very general statement. So this is the probability density, and then the entropy so entropy of the chain with a fixed end-to-end vector R can be given as kb. So basically, we're taking log of this quantity, right? So it's kb ln omega n R plus ln omega, where you have an integral over all possible drs. So all drs are allowed, and that's the total number of conformations which are allowed. Right? But in one of the previous classes, we have already discussed what is the expression for omega n R, and omega n R is 1 upon 2 pi REE and to n vector square average to the power 3 by 2 into exponential rx square plus ry square plus rz square by 2 REE whole square, right? Where basically this quantity is nothing but r end vector square, right? So you can replace this by r vector end-to-end vector square, right? This is the mean, and this is for a particular value of R. So this is the distribution, right? And just to remind you, R EE whole square and expectation value was NB square by 3, where N is the total number of monomers in the chain. Okay, so basically now when this entropy, right? So I'm just putting this back in this equation. So this equation is, I'm using this expression for omega, and if you put it back and you take the log of this and this term, and of course this remains, So then basically what you have is S and R is KB into omega nr over all possible values of r plus 3 by 2 kb ln of this term, and this has a fixed value nb square by 3 uh, minus half kb r square by ree square expectation value. Now this is a constant, so the total number of conformations is fixed, right? So it's sum, and this quantity is fixed. So S and R, the entropy with n monomers, correspond to n-to-n vector of R is some fixed number minus 3 by 2. So I've put the expression for this here, 3 by 2 kb r square nb square. So what does this say? So when r vector equal to 0, then you have the maximum entropy. And any finite value of the n-to-n vector Re, right, decreases the entropy. Now I said that all the conformations have equal energy, which is 0. So you can also write down the free energy. And free energy is nothing but U minus T. So free energy with n monomers corresponding to a particular n-to-n vector. So that you can write it as U minus T, S, and R, right? So this is the free energy for with a constraint. So there's a constraint free energy. You have put that, okay, this is what my n-to-n distance is going to be, right? And but U is equal to 0, the internal energy is equal to 0. So basically, if you substitute the formula here, what you get is the free energy becomes 3 by 2 kBt, because the T comes here. So this was because it's Ts, so T comes here, R square NB divided by NB square minus T, so constant. It's basically some these other terms. What does this say? So it again says that if R has a finite value, if the n-to-n distance is anything but 0, then basically the free energy increases, because the lowest value would be this, right? So any finite value of R leads to an increase in the free energy cost, and one can think that basically when the n-to-n distance is 0, then it has the maximum number of possible conformations, and this is what we had discussed when we were talking about the random walk polymer chain, right? That when n-to-n distance is 0, then you have the maximum number of paths which are possible, um, so that the random walker comes back to its like starting point. Right? This corresponds to that physics. Anyway, so F and R, so finally I have just rewritten the expression from the previous slide, and remember that free energy is a thermodynamic quantity, yes, but taking energy from the bath, there can be local fluctuations from the free energy minima. So this is the minimum free energy, so it can take energy from the bath and explore different conformations, right? And alternatively, basically, the polymer can also be kept at a fixed R. So basically, I already showed that if the end-to-end distance is not 0 but some finite R, there's an increase in the free energy, right? And as a consequence, the system would like to go back to a conformation where the free energy is minimized. And however, if this is prevented, you shall need to give an externally applied force F, which is very much like the pressure when you talk about the ideal gas. Now, this force X, the X component of the force, is basically the derivative of the expression for the free energy with respect to S, with respect to X, right? So when we talk about the pressure, we also talk about del F, del V. So this is corresponding to that. So there's the generalized force, if you like, and then you can similarly write down. So if you want to maintain the end-to-end distance at a finite value of non-zero Ry, then the force that you have to apply is Fy equal to del F del Y, and here the force is del F del Z, right? So this is the force that has to be applied to keep a finite value of the end-to-end vector R. In general, in 3 dimensions, the F vector, the force vector, can be written as 3 kbt by nb square into R vector, right? So you're basically taking the derivative of this with respect to Rx, Ry, and Rz, right? And this in turn can be written as kbt by Ree square average, because nb square by 3 is nothing but Ree square. So this is the force that you are applying to keep the polymer stretched so that the system is at a higher free energy than the free energy minima. One can also talk that the polymer then applies a force in the equal and opposite direction, right? So if you like, the restoring force is minus kbt by Ree square mean into X. This is the X component. Now, this looks very much like the spring constant of a harmonic spring, right? With the spring constant of kappa equal to kbt by Ree square expectation value. So this kappa, this harmonic spring with the effective entropic spring constant, has this value, as you see. And basically, so this what it says, that if you have to keep a polymer chain slightly stretched so that the end-to-end distance, the mean end-to-end distance, is greater than the end-to-end distance is kept fixed at a certain value, then a finite non-zero value, then you have to apply a force. Now this relation, let me tell you, it applies only for small deformations. Uh, what happens for large deformations, we again will be discussing after 2 classes. And this force has to be applied because it is decreasing the entropy of the polymer coil. So basically, by applying this force, we are doing work against entropic forces. And most interestingly, the kappa, the so-called spring constant, has kbt sitting in its expression in the numerator, the expression for the numerator. What does it mean? It means that if you increase the temperature, the spring constant, the energy, the force required to stretch a spring, stretch a polymer chain, or the end-to-end distance of a polymer chain, is going to increase. So you have a spring whose spring constant depends upon temperature. It actually hardens. The spring constant increases with temperature. And note that this is very different from what you see in a metal. So if you have a metal bar where you have basically atoms sitting in a crystal, if you increase the temperature, the amount of energy, the elastic moduli, actually decreases with increase in temperature, because basically as you increase the temperature, the atoms can basically move around its energy minima, right? And it takes less energy to pull the metal rod. Here you see it's happening exactly the opposite. As you increase the temperature, the elastic modulus, if you like. I mean, suppose you have large number of polymers entangled and so on and so forth. Yes, I know that we are discussing of a polymer, single polymer chain, but the same physics can also be extended when you have a dense melt of polymer chains, something like a rubber, where basically what is rubber? It's basically large number of polymer chains which are cross-linked with each other. And then this N will basically refer to the number of monomers between crosslinks. And in a rubber, actually, the elastic constant increases with increase in temperature. So this phenomena, though we have been discussing, yes, I know of a single polymer chain, but wherever you see spring constants increasing with the temperature, the generic phenomena is referred to as rubber elasticity, and that happens because the elasticity is coming not because that you're working against the energy, you're increasing the energy between the atoms, but here you are working against an entropic free energy cost. So if the restoring force increases with increasing temperature, you know that basically stretching the polymer, stretching that material is providing an entropic cost, which could be coming due to polymers, and this is the work. And this is basically happening because in a in a stretched state, there are fewer conformations for the polymer to explore, right? So that leads to a decrease in entropy, or an increase in the free energy of the system, and that is what is leading to the entropic, to the spring-like reaction, restoring forces. The system wants to go back to a state of maximum entropy or a minimum free energy, right? So this was a very brief discussion on the rubber elasticity like uh, behavior of a single polymer chain. I emphasize again, in a rubber, you have cross-links monomers. Here we have been discussing of a single polymer chain, but the physics is the same, where in a rubber, this elasticity comes from the number of monomers between two cross-links. Anyway, so now moving to a slightly different topic. So till now we had been basically discussing this part, the entropic forces when you or the free energy costs for a stressed polymer configuration. Now we're going to move to this part and then discuss the Flory theory essentially, right? So now we shall discuss about incorporating repulsive interactions due to overlap, excluded volume interactions, if you like. And I will just remind you about the pervaded volume of a polymer chain, and that an estimate of the pervaded volume is obtained by end-to-end distance tube. So that's our end-to-end distance. REE is basically, if you remember, the statistically averaged end-to-end distance square, um, right? And if you take the square root, you will get REE, and if you take the cube, 4 pi by 3 r cube, so that gives you an estimate of the pervaded volume. Yes, I remember in the last class I said that RG is a better estimate of the size of the polymer chain. Yes, you can use RG as well. If you're talking about linear polymer chain, then RG equal to REE by root 6, as I showed. And then if you take its whole cube, basically root 6 is some number slightly greater than 2, and you take its whole cube, you'll get something. I mean, the pervaded volume will change by a factor of 10. right? Now, the density of monomers from a single chain is basically the number of monomers within that pervaded volume. Yes, I know I have ignored the prefactor because we are doing a quick uh, estimate, right? So this is the bit of, I mean, you drop out the prefactors, you want to see how certain quantities, how the end-to-end vector changes with the number of monomers, which for the ideal chain was n to the power half, right? So you often drop prefactors. So this is like the scaling theory because you're more interested in the exponents, how certain quantities change with n, and you're interested in the exponent because that decides what is the macroscopic physics which is going on um, inside. Yeah, so that's how we are looking at it. So here we are dropping the prefactor. So an estimate of the density of the monomers from a single chain is around n by ree cube. Now the probability of a monomer of volume v overlapping with another monomer, right? So you have a monomer, and what is the probability of overlap with any other monomer? And that will be, of course, dependent upon the density of monomers. So the amount of volume which is excluded to this monomer or particular monomer, say, is proportional to V, the excluded volume of all the monomers, into the density, right? And so So this is the probability of a monomer of volume V overlapping with another monomer. So, and the interaction potential energy is order of kBt. See, so what is the energy? So, on an average, the kinetic energy of each monomer is about 3 by 2 kBt. So, if two particles come in contact, this kinetic energy will be converted into potential energy, and and by that they will overlap, right? And and then they will basically move away, because if they repel, all the kinetic energy can be converted to potential energy and get into an overlap state. But after that, this potential energy, there will be enough repulsive forces, so basically the particles will move away. The potential energy will be again converted to kinetic energy, and they're going to move and try out different conformations. So basically an estimate of the interaction potential energy per monomer is the order of kBt. Now, the mean potential energy per monomer, right? So the each monomer is interacting with other monomers. Now you have an idea of the probability and estimate of the probability of interaction of one monomer with the other, and the mean potential energy will be the probability of contact into kBt. And if you want to, and of course there has to be some appropriate constant, right? So the what I wanted to say here, that the probability is proportional to Vn by r cube. The mean potential energy per monomer will be proportional to or equal to some constant into kBt into Vn by r cube. Now, each monomer on interaction with other monomers could have uh, this amount of energy into a constant. And if you have n monomers in volume Vp, pervaded volume, then basically the potential energy for n monomers would be this value into n, right? And this constant into V, you can replace it and write it as V dash, right? So basically we'll say that the mean potential energy for n monomers is proportional to kBt into some V dash, constant into V, into n square by r cube. And that is exactly an estimate of the potential energy of overlap of monomers. And the Flory theory basically does a rough estimate of the overlap energy, which is exactly what we did. And before that, we have been discussing about the entropic free energy cost. And the Flory theory tries to balance the overlap energy, which tends to swell the chain, and the entropic energy, which penalizes a polymer conformation which is more swelled, right? And a balance of that will give you an estimate of the size of the polymer chain when you have incorporated the energy for overlap. So the total free energy will be the free energy due to interaction plus the free energy due to entropy, and that is equal to kBt. So from both, you have the V dash n square by r cube, and that is the estimate of the overlap energy. And the free energy cost for swelling is basically r square by nb square, and if you wish you can keep the this prefactor of 3 by 2, but you can also drop it, right? But note, when we are using this, we are using the ideal chain expression for the entropic free energy cost. Now the optimum size, okay, so this is the total free energy, the energy cost plus the entropic cost. And the optimal size of the polymer chain can be obtained when this free energy is minimized. So basically the optimum size is basically the Flory size or the Flory radius with the f in the subscript, and that can be obtained by putting del f del r equal to 0, and that is exactly what we do, and take the derivative with respect to r. And when you take the derivative with respect to r, these are the terms that you get, right? There was already r cube sitting here, and if you want to keep that prefactor, you want to keep this prefactor, well you can, but that is often dropped, but I've just kept it for your convenience so that you don't get feel lost. So this derivative, this expression is equal to 0, and if we just adjust the terms, there are only two terms, one with a negative sign, one with a positive sign. What you get is r f to the power 5 is v dash, it's basically all the constants, the prefactors, excluded volume, all is clubbed inside v dash, b square into n cube. So rf, the Flory radius, essentially goes like this expression, some constant, v dash b square, and if you keep these three term, this 3 will also remain, to n to the power 3 by 5. Message: the size, an estimate of the size, the radius of gyration, if you like, right? The end-to-end distance, square average, and you take the square root, which gives you an estimate of the size, was going as n to the power 3 by 5, sorry, n to the power half for the ideal polymer chain. However, when you include the excluded volume effects, this RF goes from half to n to the power 3 by 5, 0.6, right? And this is for polymers with excluded volume interaction in good solvent, and this gives you an estimate the size of the polymer of the chain. Now you say that, okay, it was n to the power half, 0.5, instead it has gone 0.6, 3 by 5, which is 0.6, and why should you care? Let me tell you why you should care. Now suppose you have a very long polymer chain. 1 million is a very standard size of a polymer chain. It's not particularly long. So if you take 1 million to be n, then n to the power half, square root of n, is 1000. You can use the calculator and take 3 by 5 exponent of 1 million, and you will get the answer 4,000. So basically the radius has increased by 4 times. So the polymer chain is 4 times bigger. But now just consider the pervaded volume, which is r cube. The radius was 4 times bigger. The pervaded volume is 64 times bigger. And that is just talking about a normal polymer chain with 1 million monomers. So it has actually increased in size 64 times. So basically, something which we would call a dilute polymer chain is now a semi-dilute, and that would lead to serious consequences in terms of the properties of the or the dynamics of the polymer solution, which we have not come to yet, right? Just to summarize, for an ideal chain, you have R, an estimate of the size, goes as n to the power half. R goes as n to the power 3 by 5 with excluded volume, and that is exactly what is seen experimentally. And this is called the so-called Flory exponent. Now, there have been much more accurate theories with much more details put in, and with RG and exact enumeration and so on and so forth. So more complicated, involved theories predict this Flory exponent to be 0.588 or 0.59, which is very close to this 3 by 5 that we get with a very uh, quick estimate, the mean field estimate of the free energy costs, right? Uh, so this is what the Flory theory is. But just before ending this lecture, I want to emphasize, yes, the Flory exponent is 3 by 5. This is what we see in experiments also for a dilute polymer chain. But want to remind you that this was a mean field theory, and that we got the Flory exponent to be 3 by 5 is by a lucky cancellation of errors. So there were some approximations, there were some errors we made, which I need to highlight and point out. And one of the things is that the repulsive interaction due to overlap is actually overestimated in in the Flory theory. Okay. Uh, so in the Flory theory, basically the repulsion interaction goes as V, some constant excluded volume or renormalized excluded volume into constant, and squared by R cube, right? And if you put it back, and square R now goes as 3 n to the power 3 by 5. And this would give the, I mean, if you put it in, you would see the repulsive interaction essentially increases with the number of monomers in the chain. It goes as n to the power 1 by 5. So if n is more, repulsion interaction increases. But actually, the interaction energy goes down with n in reality, if you do a more detailed, more accurate calculation. And you can see that because we saw previously that the concentration of polymers inside VP actually falls as n to the power half, right? For an ideal chain, the density becomes less. As a consequence, the probability that a monomer along the chain will see or overlap with another monomer, which is far away along the contour but part of the same chain, also decreases. In fact, in section 2.7, page 78 of Rubinstein and Colby, it is shown that the probability of contact between two monomers, which is s distance away along the chain contour, falls as 1 by s, right? So, I mean, if you like, so there is less probability of contact as the chain becomes long. So you cannot say that the repulsion interaction energy is goes as n to the power 1 by 5. What is the consequence? So there's not so much repulsion. As a consequence, the chain will not swell as much. The free energy cost for swelling is not, we have overestimated it, right? So it won't swell that much. Furthermore, so the repulsion interaction is overestimated. Moreover, even the ideal chain entropy is assumed, and this is an overestimation, right? Because when we are using the ideal chain entropy, we are taking all possible conformations of the chain to figure out one estimate for the ideal chain entropy when it is stressed, and so on and so forth. In practice, much fewer conformations will be allowed because chain passing won't be allowed, and so on and so forth. There's a finite size of the polymer monomers, and so on and so forth. So again, we overestimate the polymer chain. So the force which is there to contract and get it back, right? So if you stretch it, there is a certain energy, free energy cost to it. So that is overestimated. The repulsive force is also overestimated, and luckily it has been shown by more detailed calculations that when you calculate what is the extra contribution due to this uh, repulsion interaction which has been taken into account, and this extra contribution which will try to shrink the chain, they actually exactly cancel. So that we got the correct exponent of 3 by 5 is due to a lucky cancellation of errors to give the correct Flory exponent of 3 by 5. So much more detailed calculations also give mu equal to 3 by 5, but such a simple mean field theory, Flory theory gave the right exponent is due to a lucky cancellation of errors. But at the same time, this Flory theory has all the right ingredients in terms of rubber elasticity or the entropic forces or an estimate of the overlap, the energy cost due to overlap. So this is a simple theory, yet it gets the right answers. The physics is nearly right in terms of the contributions are right, the calculations, the details, yes, both are overestimated, and hence Flory theory is a very good starting point to understand that a real polymer chain with excluded volume interaction actually swells and has an estimate of the size which goes as n to the power 3 by 5. Okay, so so this is where we will stop this part of the class.